Hey everyone. In this lesson, we're going to talk about how two planes can intersect, and we'll actually start talking about how three planes can intersect too. So let's get started. So starting with two planes, how can two planes interact in R3? Well, there's three possible cases when you have two planes in R3. And the first case is if the plane's two normals are not parallel, then you can kind of visualize that they're going to meet in a line. It's kind of cool. And I want to emphasize a couple things on this diagram here. So if you have the normal for that plane and the normal for that plane, the important thing there is the normals aren't collinear. And they intersect in a line. The other two cases are a bit less interesting. So in the second case, the two planes are identical, or we could say the planes are coincident. And we've been saying, there's infinitely many solutions. They intersect everywhere. Something like that. Let's just say infinitely many solutions. And then there's the case where they're parallel and distinct. And just like two parallel lines, they'll never meet. Parallel and distinct, they never meet. So you can have no intersection like case 3, or they can intersect everywhere like case 2. But in case 1, when there isn't intersection, with two planes, they're not going to intersect in a point. Two planes intersect in a line. And so we want to talk about how can we find the equation of that line, or an equation of that line. So here's the first example. So whenever you're looking at the intersection of two planes, the first thing you want to look at is, are the planes parallel? So you definitely want to check that out first. And so here we can see that N1 is 2, 4, 6, which is exactly 2 times 1, 2, 3, which is 2 times the normal for the second guy. So because these planes are parallel, or because the two normals are parallel, the planes will be parallel too. So the answer is yes, because the normals are parallel, collinear, whatever you want to say. Well, now let's see if they're the same plane or not. Let's reduce pi 1 by dividing everything by 2. We get x plus 2y, excuse me, plus 3z minus 6 equals 0. So now you can see that pi 1 and pi 2 are parallel. They have the same normal, but their d values are different when the other three coefficients are the same. So these guys are definitely parallel but distinct planes. And we can just say no, they are distinct. Excuse me, got some in my throat. So I want to show you guys what happens if you actually just try to solve this linear system. So if you take the reduced pi 1 and pi 2, imagine we used elimination like back in grade 10, and we subtracted, say, equation 1, and we did equation 1 minus equation 2. So what would we get if we did 1 minus 2? Circle was in the wrong spot. My tablet's being funny. 1 minus 2. Well, you do x minus x, you get 0. You get 2y minus 2y, you get 0. 3z minus 3z, you get 0. Negative 5 take away negative 6 is 1. And on the right, you'd have 0. 1 equals 0 is never true. And we saw cases like this when looking at how two lines meet, in this or a line in a plane. But when you get a statement like this, that means there are no intersection. There is no intersection. There are no solutions. So our work from A, B, and C is consistent with what we found in D. Let's look at a second example. I'm just going to do one big one and hopefully I get it out. Probably not, but let's look at these guys here. So here we have two planes, but right now one's in Cartesian form, one's in vector equation. So to compare their normals, we'd like to find the scalar equation of pi 2. So this is just a good exercise if you want to pause the video and try that. We want to find the normal. So we have been doing the cross product of the two direction vectors. 1, 1, 1, 1, 2, 3, 1, 2. And that cross product would be 3 minus 2 is 1. 1 minus 3, negative 2, and 2 minus 1 is 1. 1 minus 2, 1. The scalar equation would be x minus 2y plus z plus some number d equals 0. Plug in your point. I chose an easy one. 1, 0, 0. 1 minus 2 times 0 plus d equals 0. So 1 plus d equals 0, or d equals negative 1. So here we have the plane pi 2 is x minus 2y plus z minus 1 equals 0. So now we have the scalar equations. If you notice pi 1, its normal is 2 minus 4, 2. We can reduce that so we can make a comparison. If we divide everything by 2, we get x minus 2y plus z minus 1 equals 0. And now you can see that, hey, these are actually the same plane. So we can say they are the same plane. And you could say they intersect everywhere, or they're infinitely many solutions, whatever you want to use there. They intersect everywhere. But that wasn't obvious when looking at the originals. We had to put them both in their scalar equations in order to compare. And once we did that, it was easy to see. So we've covered now case 2 and case 3. So if you look at these two guys, clearly the normals here are not collinear. So these two planes are going to meet in a line. And how can we find the equation of that line? So I'm going to show you guys. So remember, the equation of a line is not unique. So if I do it one way, or you do it one way, and your friend does it a different way, you might have two different looking lines that can both be correct. But we have developed tools for you guys to check if two lines are the same. Whichever way you slice it, our direction vectors should be collinear, because no matter, we're both going to find the same line. And my direction vector should be parallel with yours. So the idea here is, with three equations with two equations and three unknowns, the best we can do is eliminate one variable to get one equation with two unknowns. So in this case, I'm actually just going to eliminate the z's. So I'm going to multiply pi 1 by 2. So 2x minus 8y plus 2z minus 6 equals 0. So hopefully you would agree that's just plane 1. It's the same plane. I just scaled everything up by 2. And now I can eliminate the z's. So if I don't even need to do that really, because I had pi 2 and pi 1. That could be confusing actually. So I'll just erase that. So what happens if we do pi 2 plus pi 1? So that's going to eliminate the z's. You'll note that I could have subtracted and eliminated the x's, but I'm just going to add those two planes together. And what do I get? I get 4x minus 6y minus 9 is equal to 0. And now I have just a new equation, but with only two unknowns. But the idea here is, from here, I can actually make, the equation of my line. And here's how we do it. we start off, if you recall, when we found the vector equation of a vector equation and parametric equations for a plane, given the scalar equation, we just used a clever trick and just made up a simple parametric equation to start. And I'm going to start with this way. I'm going to say, hey, the first parametric equation for my line is y equals t. And maybe we'll talk about the significance of what that means after, but you just parameterize one of your variables. Let's set y equal to t. So then we have 4x minus 6t minus 9 equals 0. And that gives us an easy way to get a parametric equation for x. So we just rearrange for x. So we'll have 4x equals 9 plus 6t. And dividing by 4, I get x is 9 over 4 plus 6 over 4, that's 3 over 2t. And now I have a parametric equation for y, a parametric equation for x. All I need is a parametric equation for z. And I can get that by taking my y equals t and x equals 9 over 4 plus 3 over 2t. And I can plug that into any one of my planes to get only z and t. And then I can solve for z. So I'm going to sub this into, let's say pi 1. That looks easy. So I get 9 over 4 plus 3 over 2t minus 4t plus z minus 3 equals 0. And we have to solve for z. So maybe you don't really like working with fractions. We got to deal with that. That's okay. But, so if you're not comfortable just adding fractions together, we can clear the fractions. If you multiply everything in this equation by 4, you get 9 plus 4 times 3 over 2, that's 12 over 2, that's 6t, minus 16t plus 4z minus 12 equals 0. And now there's no more fractions. And so we get 6, 10, negative 6t minus 3 equals 0. And why am I solving for t? I have my z's there. You have to forgive me. I thought that z was a t for a second. If you were screaming at your computer, I found the mistake. Just got over anxious there to solve that equation. Yeah, sorry, we can't collect the t in the z terms. That'd be silly. So 9 minus 12 is negative 3. 6 minus 16, that's negative 10t plus 4z equals 0. So 4z equals 3 plus 10t, or z equals 3 over 4 plus 10 over 4, or 5 over 2t. And there's a parametric equation for z. So in principle, it's not that hard to do. You eliminate a variable and then make, with the resulting equation you have left, 2 variables, you make one of them a parameter. Get your second parametric equation by solving for the second guy, and then plugging both back into one of the original planes and solving for z. So the math we're using is just kind of grade 9 stuff, just rearranging, clearing fractions. We can do it. So we've got it. So here's our line. So for the line of intersection, you can write the parametric equations. So 9 over 4 plus 3 over 2t, and y equals t, and z equals 3 over 4 plus 5 over 2t. If you want, you can write that as a vector equation. And I might just move that up here. For a vector equation, but the vector equation corresponding to these guys, we get the point 9 over 4, 0, 3 over 4. Plus t, 3 over 2, 1, 5 over 2. And so when we chose that parametric equation y equals t, we were letting the point on our line of intersection be 0 and the direction vector component for y to be 1, and then to figure out what the rest was. Now, you could simplify this a little bit. You can't just like multiply the points by 4. 9 over 4, 0, 3 over 4 is a point on that line of intersection. If you multiply it by 4, 9, 0, 3 wouldn't be on the line of intersection. So you can't do that, but you can multiply if you would rather use a direction vector with whole numbers. We could multiply all the direction vector numbers by 2 and get 3, 2, 5. That would be, maybe I'll say or. That would be fine as well. That's the math behind finding a line of intersection. Eliminate a variable, choose a clever parameter for one of your parametric equations, and then it's just a bunch of rearranging and solving from there. Right, so that's two planes, how they can intersect. We looked at all three cases and what happens with the math. How can three planes interact? So I believe your practice for today from this lesson is only two planes, but I wanted to get a bit of a head start on three planes just to save us. So I only need to do one more lesson on this. So when considering three planes and how they can intersect, there are three possibilities that actually give you some kind of meaningful intersection. And when there is a meaningful intersection between all three, we say that these systems of three planes are consistent. They have a solution. In case one, three planes can have a point of intersection. So case one is there is a single point of intersection. Case two, you can see if they're arranged that way, there is a line of intersection. So it is possible for three planes to be oriented in some way that they meet at a line, and I think that visual does a good job of showing that. And in the third case is when the three planes are coincident planes. That wasn't spelled correctly. Coincident. They meet everywhere. So that's kind of the uninteresting case. These two are interesting though. So how can we tell which is which when there's going to be a point of intersection and a line? But if you look at case two, and if you can imagine the normals, what's cool about this situation is if three planes are going to meet in a line, their normals have to be coplanar. Their three normals will lie on the same 2D plane. So in this case, the normals are coplanar. And if you recall, we actually have a tool for figuring out if the normals are coplanar. See, if the normals are, say, not coplanar, oh, I'm going to test my drawing skills here. If the normals weren't coplanar, remember that they formed a 3D shape called a parallelepiped. If the three normals are coplanar, then they don't really form a 3D shape. The best they can do is form a 2D shape, and that volume would be 0. So we'll look at that triple scalar product later as a tool to help us see which case it is. In the case of a single point of intersection, the three normals are not coplanar. So the three normals will kind of form a little 3D region of space like I drew here, and they'll give a parallelepiped with a non-zero volume. So we'll come back to that tool later, but those are the three cases visually of what happens. How can three planes interact? So these are inconsistent systems. So these are the three cases where you have three planes and they don't meet. So the first case is that all three are parallel and distinct. Parallel and distinct. And there is no intersection. And you guys know how to see this. You put all three in Cartesian form, check the d values. It's pretty easy to see. In the case of two of them being the same plane and one is not, we've already covered that case really when there's how two planes can interact. Case two is that two of them are parallel. And distinct. You still get no intersection, right? The third plane that's not parallel, it's going to meet one of the planes in a line, but it'll meet the second equation in another line. But there's no common intersection between all three. And the third case is it is possible for three planes to not be parallel and for them not to have a point of intersection. And that's case 3 here. In this case, it's kind of like case 2 in the previous slide. The normals are coplanar, but the planes are arranged in such a way so that there is no intersection. So there's 3 cases where the planes are not parallel. And that was case 1, case 2 in the previous slide here, and case 3 in this slide. So if your planes aren't parallel, you can't make any conclusions yet. And also, if you do a triple scalar product, we'll do that later, and you find that the 3 normals are coplanar, you actually don't know whether it's a line of intersection or no intersection until you do a bit more math. In the case of the planes are not parallel and you do the triple scalar product and you get some non-zero value, then you know there's a point of intersection. But yeah, so if you determine this triple scalar product and you get 0, you actually don't know what it is. You've narrowed it down, but you have to do some more work. So we're just going to talk about that right now. We're going to do, so the big idea is hopefully you've got this idea, is that, basically you investigate the normals and it tells you how the planes are going to meet, or at least it narrows it down. So the triple scalar product can narrow down how 3 non-parallel planes would meet. Obviously, it's easy to check if normals are parallel for those other cases. And remember, the triple scalar product is the following. You take the 3 normals and you do the cross product of 2 of them and dot it with the third. And this gave you the volume of a parallelepiped formed by the 3 vectors. And again, if you get 0, that means that the 3 vectors form a 3D area of space with no area, i.e. just a single parallelogram like here. And they're going to be coplanar. So let's just try that right now. So these are some obviously these 3 planes are not parallel. None of them are parallel with each other. So we want to see, are they going to meet in a point, a line, or not at all? So to do that, we need the triple scalar product. So let's do N2 cross N3. I'll do that in the space down here. So N2, we do -1, 1, 1, -1. And then pulling off the normal for pi 3, it's 2, 1, 1. So that would be 1, 1, 2, 1. The cross product between those is -1 subtract 1, -2. 2 subtract 1 is 1. 1 subtract -2 is 3. And so N1 dotted with N2 cross N3 is 1, 1, 1 dotted with -2, 1, 3. I get -2 plus 1 plus 3. And I get 2. So what this means is these 3 vectors, and I'm not sure this is how they're arranged, but those 3 vectors form a little 3D region of space. That's fine. Which means they're not coplanar, which means this is case 1. So since N1 dotted with N2 cross N3 doesn't equal 0, we can say there will be a single point of intersection. Now, the math behind finding that point of intersection we'll do in our next lesson, but now we've at least got it set up where we kind of know how to narrow down which case it is. Let's look at the next example here in B. So in this one, I'm going to have you guys just maybe pause the video and think for yourself which case this one is, and then unpause when you're ready. But I'm going to go along. So hopefully, before reaching for the triple scalar product tool, you guys would have recognized that pi 1 and pi 3 are parallel and distinct. Those two planes. Those two guys are parallel and distinct. So what we have here, and then the second plane is not parallel to either of them. So we don't need to do any work. We know that it's case 2 in this inconsistent system slide is that there's going to be no intersection. So no need to do the triple scalar product. We know which case it is. So be smart, look at the normals, see if any of the normals are parallel. Because if you can determine that, often you can just reason out if there's an intersection or what case it is. It's when they're not parallel that you need to do a triple scalar product and check. Now, I'll just say one more thing about this example 4 here. What if we did get 0? What if we found out this was equal to 0? Would that mean like it was not 0? So we know it's a single point of intersection. But what if it was 0? Well, if we go back to our 3 slides here. So remember, if the normals are coplanar, then n1 dotted with n2 cross n3 would be equal to 0. The same thing happens here. n1 dotted with n2 cross n3 would be 0. In the case where the triple scalar product is 0, you don't know whether it's consistent and you have a plane of or line of intersection, or it's inconsistent and there's no intersection. You have to do more work. But that'll be a job for tomorrow or our next lesson. Tomorrow for me when I shoot the lesson, whatever for you guys. All right, so the work I've given you there is just looking at 2 planes and finding lines of intersection. But we have done a lot of the heavy lifting and legwork so that we can just focus on kind of the algebra in our next lesson on how and finding the point of intersection, if there is one, between 3 lines. All right, guys, that's it for this lesson. Hope you're staying well. Have a great day, and we'll see you soon.